Hello, everybody, and welcome to the second Rust Graphics Meetup. We ran the first one several months ago, and it was a really cool opportunity to have more focused talks from the community. And so I sort of wanted to try this again. And I've also heard from a lot of people that it's like a really great opportunity to kind of like show off their own stuff. And so I want to see more initiatives like this, and I'm going to keep pushing forward with them, which is why today we are here with the second Rust Graphics Meetup. So a little bit about myself. I'm one of the leads of the Rust game dev working group. I work on a game called Valorant, but I do not know that much about the graphics ecosystem. And so I have someone here with me, Connor. I'll let you introduce yourself.
Yeah, my name is Connor, also known as CW. I am the co-maintainer of Wgpu, the Rust graphics API, and I also make a library called Ren 3, which is a 3D graphics rendering library. And yeah, I will be. Oh, go on.
Oh, no worries, no worries. So I am here today as like sort of like the logistics person and everything, but there's a lot of questions that I found. I'm okay at asking questions, and I love reading questions from chat, but I do not know about enough about the graphics ecosystem to really get into the nitty gritty. And so Connor will be helping us a lot with that today. And Connor, I'll let you talk a little bit about how that will go.
Yeah, so if there are any questions for any of the speakers at any time, that is my cat. Please just drop them in either the YouTube or the Twitch comments. I will be able to see them, and I will pass those questions forward when we get to the question time.
Perfect. Sounds
audio
good. So,
problem.
Wait, is there an audio problem? I think audio's all right. Cutting out from speaker. Connor, do I sound all right to you?
You sound okay to me.
All right. It could be something with Twitch. Let us know in chat if other people are having this issue as well, and we'll try to get it remediated. But without any further ado, we are going to hop into the first talk of today. And so we will be back. Oh, actually, wait, I was supposed to share this screen. I was supposed to say, ooh, we have like a fancy schedule here. And I was going to make a fancier schedule in like some presentation format, but I'll just use the blog. And so I don't even know where the screen is right now. We've got a few really awesome talks today. Some shorter ones as like lightning talks, one longer one by Connor himself, and hopefully we'll be able to see some really good content. And then just as a little bit of a reminder, everything that we're doing here is recorded, and so it will be posted to YouTube afterwards, and so you can go back and rewatch the videos. Yep. So without further ado, we will hop over to the first speaker, and we'll be back in just a second. All right, so hello. We are here with Lukas Orsvärn, sorry, and Lukas will be talking to us about Vismut today. And so, Lukas, I'll pass it over to you.
All right, thank you very much. Yeah, so like was said, I'm Lukas Orsvärn, and I've been working on this tool called Vismut for a while. And it's a node-based procedural texturing tool. And I'm going to talk about how I recently rewrote the backend for, I don't know, like the 4th or the 5th time to fix some issues. So I'm going to talk about what the issues were and how I fixed them and what I learned. And this is an adaptation of a blog post that I wrote. All right, so before we get into it, let's talk about some words, so you know, so we're on the same page there at least. So this is a graph that you're seeing, and a graph is just a collection of nodes and edges, with an edge being a connection between two nodes. And in Vismut, I'm dealing with DAGs, which are directed acyclic graphs, which means that they're graphs that go in one direction, so they don't have any relationships going backwards. And they're acyclic, meaning you can't have cycles in them or loops. And they're graphs, so they're DAGs. So in the old architecture, I had a shared memory setup. So we have the GUI thread loop going, doing its own thing at 60 frames per second or whatever, and then we have the engine loop doing its own thing. So the way it worked was when you created, like when you instantiated or whatever, the engine data struct, it would also spawn an engine thread loop on its own thread that would always check the engine data every loop. And if it saw some change, if something had happened, it would start processing the nodes or whatever, do what needed to be done to make the output up to date. And the idea with this architecture was to make it so that the GUI would never have to wait for the engine to do something, so the GUI would be smooth, which is really important for me. I value like the user experience a lot, and I feel like having a user interface that's always responsive is that's like a very basic thing there that I really want to have like built from the beginning. This architecture caused some issues though. So first off, maybe the user doesn't want to run the engine update in its own thread. Maybe it wants to run it on the main thread or in some thread pool or something, I don't know. But in this architecture, it's like, no, it has to be done like this. You can't choose it. So that's not so good. Also, the types and the code that you had to write when using the library was kind of annoying. For instance, just to get some data from a node, you had to write something like, you had to first like lock the engine itself, and then you had to get the node and then lock that node, and then you had to get the data from the node and then lock that data. And then you could like read and see what's this float on this node. And in the new architecture, that's just instead, you get the engine, you want to get the node, and then you have it essentially. So it's much easier to read, much easier to write. It also caused a bunch of timing bugs. So since there are two threads working on this at the same time, things like the following could happen. Let's say that the GUI thread adds two nodes and two edges between the nodes. So the engine thread would see this and it would be like, oh great, there's something for me to do. And it would start processing the things. And as part of that, it would go through its things to do, right? And it would see, oh, there are two edges going into this node. That's good to know. So it would take those two edges. And now, at this point, the GUI thread comes in and because the user just added a new edge. So it adds a new edge. So now there are three edges connecting these two nodes. But the engine, nevertheless, keeps doing its thing. It creates a package for processing, sends that to a thread for processing, and then later on it gets the result back from the thread, which is the buffers that are generated. And it would say, oh, I see these threads belong to this node. It would mark the node as done, and everything is great, except it's not great, because the user added a third edge, and now we're in a state where the node is marked as done, but the graph itself does not reflect the new edge that was added. And so these sort of like timing bugs, there were a lot of them. And what I did to try and fix them was, instead of, when the engine was processing, instead of just getting a tiny lock for a short amount of time, just getting the edges, for instance, I would have to take a lock at the beginning of the processing and then hold that lock until the processing was done, essentially. So I would extend the amount of time that the lock was held. And despite trying this to make this happen, to fix these bugs, I couldn't ever actually fix all of them. Like I still had that one bug that happened like 1 or 0.5% of the time, where the node, like the output of the graph, didn't match with the graph itself. So that was really annoying. And as a result of making these lock times longer, also on the GUI side, that means that the GUI couldn't get its locks as easily. So you can wait for a lock on the GUI side, But I don't want to do that. Like the entire point of this architecture was so that I wouldn't have to wait for locks, that I would always be able to get it almost every frame at least. So instead I try to get a lock, and if I can't get one, oh well, I will try again next frame. But that doesn't work very well when you extend the locks to hold them for an extended period of time, because then the GUI couldn't get locks several frames in a row, perhaps. And then that meant that maybe an output was finished, but the GUI couldn't get a lock, so it couldn't display it in the user interface. And beyond that, I'm using a GUI library called eGUI, which is an immediate mode GUI library, which means that it doesn't hold any state itself. It just essentially, to simplify it a lot, it recreates the entire user interface every frame, which means that if it can't get a lock, so it can't get any data, it can't create the user interface, meaning it would flicker in and out of existence, depending on, could it get the lock or not. So with all these issues, I decided I need a new architecture. So the new architecture is, first off, much simplified in terms of it's just a struct. It doesn't create its own thread loop or anything like that. And if you want to run, if you want to process the nodes, you have to just call a function which processes the nodes. And so you get to decide when and where that happens. Here, this slide shows the engine threads and the GUI threads over time. So this is how it's working now in Vismut with the new architecture. So this shows one frame in the GUI, and the first part there is it updates the GUI in the GUI thread, and at that point it owns the engine, so it has full access to the engine. It can mutate it and read from it, etc. And when it's done with that, it sends it to the engine thread, and there the engine just gets run over and over, and while that's happening, the GUI is being rendered, and it's waiting for vsync and so on. And when the GUI comes to a point where, okay, I'm done, I'm ready to, I want access to the engine again, it just sends a message to the engine thread, and it sends it back, and it can repeat the process. And so it gets sent back and forth once per frame. So this vastly simplifies the code. It makes it more complicated in that I have to send it back and forth, but that's not so complicated. It's pretty simple code, but it makes it much easier everywhere else because you have direct lock-free access to everything when you need it. So, and more flexible as well, of course. But I didn't only make it better to use it in this way. Like, I didn't just make it better to use it from the outside. I also made it better on the inside as well. This slide shows how the internal data of the engine is split up into 3 different worlds, as I call them. So we have the public world, which is the public interface. So anything that's not in the public world isn't accessible from the outside. And this contains, it can have several DAGs in it, all containing several nodes and edges, and it can also have connections between the DAGs, like between nodes in the DAGs. And it can have nodes with DAGs inside them as well, which is an important aspect of like being able to create an entire DAG and then be like, okay, this DAG is now one node that you can use in another DAG, etc. And that's how you can build up like a library of being able to make stuff quickly and build tools with the system, So you have that, and that's what the library user manipulates. And when it wants to process it, it first calls a prepare function on it. So it calls engine.prepare, and that creates a flat world from the public world. And they are similar, but the difference between them is that the flat world contains only one DAG. So if there are 2 DAGs in the public world, or 3 DAGs, or however many, all the nodes in those will just get lifted out and put into one single big DAG. And all the nodes that contain DAGs in them will also be like expanded out into their contents. So yeah, it just flattens out everything and makes it that there's only one big DAG now. And once it's done that, and oh, I should say, by the way, the reason for this is that it simplifies like when you want to process these things, like when you're processing a DAG and it has like a DAGs inside of it, it gets pretty complicated. You need to write pretty like complicated special code to determine what happens when it starts processing a node that has a DAG inside of it. You need to do like special stuff there. Like, oh yeah, I need to like go in and like expand, like activate the DAG and then start processing it, etc. And when all is said and done, you don't even have any like granular change detection. So you can't. It's really hard to see like, oh, did just this node in the DAG change when the user changed the setting on it, etc. So this just like instead of trying to solve that problem, I have this flat world step. That just makes that problem disappear. So it's not a problem that exists anymore. So I don't have to solve that problem, which is great. This is a much simpler thing, just to flatten it, rather than trying to do special cases for all the nested DAGs and the sibling DAGs and so on. And so once the flat world is created, from that I create a live world. And the live world has a different set of nodes from the public world. And this set of nodes is optimized for being processed, or for being easy to program to be processed. And one node in the public world, or the flat world, one of the public nodes, can turn into several nodes in the live world, which allows for better reuse of nodes and so on. So that's how it's changed on the inside as well. And that's pretty much it for like how this has changed in the new architecture. And as for what I've learned here when I've been doing this, so first is think twice before using shared memory. Like it has great use cases, of course, but you should be aware of what they are, maybe. At least now I feel I know of one case where it's not good to use shared memory. And secondly, this is something I haven't done before, which is solving a complex problem by simplifying it away, removing the problem by making it not a problem anymore. Essentially, using data, like changing how the data looks to make to solve problems essentially. So that's also something that was new for me. And that is the end of this presentation. So yeah, if you're interested in more information, you can go to gitlab.com/vismut-org/vismut. You can also go to vismut.org. I don't know why I didn't put that in the slide, but yeah, that works too. So thanks for me.
Yeah, thank you for that. We got one question in the chat, which is, what are some UX decisions you've made with Vismut that make it easier for the end user to use?
Yeah, so one example I gave was to try to ensure that the user interface is always lock-free, so that it's always manipulatable. And other than that, like I haven't gotten that far into it yet, creating the program. That's also something that I should have mentioned, but I forgot to mention, is that this is still very early on. So I've rewritten it many times, and all you can do with it right now is doing like channel shuffling, where you like decide which channel is RGB and A in images, essentially. So I haven't gotten that far into the user interface yet. But the thoughts for how to make it better in the future, or how to make it good, is one example is I don't want to have the user have to deal with a bunch of. I want to put the graph like front and center essentially. So instead of having like, oh, the graph is like in a portion of the screen there, and then you have like a bar on the side there with a bunch of things, and then you have like a preview on the bottom, etc. I want that, all of that should be the graph, and then you can have like a better overview of it. And also I'm questioning like basic things like, do you really need to be able to just like scroll to any zoom level? Is that useful? Or would it be more useful to have like a minimap sort of approach where you push a button and you see all of the graph, and then you choose where you want to go instead of being able to zoom out and in. Another thing is a lot of these node-based tools allow you to place nodes wherever you want. So, you can place them like 2 pixels down or whatever. Well, first off, that's not okay for me. They need to be on a grid. And secondly, because that's not okay for me and I have to fix it so that it's on the grid, that takes up time for me that I don't want to have to deal with, spending. So I have made it so that, or I'm working on right now actually, that the nodes are always on a grid. And you don't have to worry about that, which also opens up the door for other automation things, making them simpler, where I can actually move nodes more easily because I know exactly where they are. I don't have to worry about, it's 1 pixel into above it, so should I move that if I want to move other nodes, etc. So yeah, there are a bunch of things like that. Like I'm not very happy with pretty much any node-based tools, and I've used a lot of them, and I feel like they can be better. So yeah, it's a lot of stuff like that.
Cool. I just wanted to mention that I find the advice about shared memory very interesting, and because I've also got burned by that before, where you think you think that like, oh, we'll just have locks and locks will solve all these problems, and then you go and find that like if you have to, anytime you use the thing, you have to take the lock, and suddenly the whole world's locked out, and this very message passing way ends up so much cleaner. So it's very cool to see.
Yeah, exactly. Like there are, like I'm sure. I mean, there are good use cases for it, obviously, but you really have to, like, it becomes a totally different world of errors that can occur when you're using shared memory essentially, and you need to like. I ended up also doing things where, okay, so now I'm at this point and I grabbed this information. Now I need to check again, like, did something happen to this? And I need to redo previous work because something has changed now, things like that. Yeah, it can get really hairy and hard to understand what's going on.
Cool. Well, thank you so much. And I think we will move on to the next talk unless there's any other last second questions.
All right, thank you very much.
Okay, looks like it's working. Can you hear me?
Sorry, I forgot I manually muted myself. Yes, so looks good. We're back with the second talk on screen 13. John, I will hand it over to you to get started.
Great, thank you very much. So I want to start this talk off pretty quickly because it's a lightning talk and I don't really want to take too much time just yet. So as I go back over the slides, I want to introduce myself. I've been using Rust since 2016, and at the same time I picked up Vulkan. Actually, that's why I learned Rust. But I've been doing graphics for like 30 years now, and that kind of scares me a bit too. But I've learned in this time that the community and sharing is really, really important. So recently, I got really excited because of one of the projects I saw in open source. I took up some of the ideas and I combined them with some more, and I'd like to share with you today what I'm working on, which is a graph rendering library. And every time we talk about graphs, we just did a moment ago, and we're going to talk about them now. We've all got different images in our heads. But with regards to rendering, and with Vulkan especially, which is the API that I'm targeting, I wanted to explain that rendering graphs are going to help, I believe, games automate some of the things that machines do. And in the case of Vulkan, we know there's so much weight with render passes and barriers and descriptors and pools of structures of all different types. It just never ends with Vulkan. So I think when we formulate the problem as a graph, we can eliminate some of those troubles. And I think that's what Screen 13 is doing by allowing you to directly access images and buffers and shaders, just like as graphics programmers, we are thinking and trying to, formulate our problems, but previous APIs have limited us from expressing. And so that's the kind of graph, and I'll show you on the next slide a little bit more. This is just the bullet points. But of course, with every graph, like all the different systems that are out there today, we have to choose if we're doing it, offline or online. And that affects how much memory gets used, if it's something we can change, if the graph can make modifications, or if it's the case where a render graph can only have parts turned on or off. So let me go to the next slide and show you a picture, which may kind of help illuminate some of the stuff that we were just talking about. So a typical game might have a graph that takes a number of operations that we'll logically think about as, shader calls with inputs and outputs. And they all formulate together into usually some sort of post-processing that appears on the screen. So the goal of Screen 13, when I created this library, was to make this process that you're looking at on the screen just a little bit easier, because there's a lot of boilerplate with Vulkan. And so on the next slide, I've got a picture that shows you some of the GLSL code you might write, the shader code for Screen 13. And this is just like any other engine where you write a shader and you put a bunch of images and buffers into it. And beneath that, I'm showing you a usage pattern with Screen 13 that allows you to compose a graph. So this little section of code right here would be equivalent to one of those tiny blocks on the previous screen, such as convolving an image or doing a blur pass or something that might be related to some step of the rendering. This one here is a fur and lava shader, obviously. So you can kind of see it's a pretty simple library as far as the presentation, but it's also pretty basic, which is very much where this presentation is at the moment. I'm kind of looking for community feedback on where to take the ideas in the library. And yeah, I guess that's pretty much the entirety of my lightning talk. So I guess I'm done.
That's really cool. Thanks for sharing. So we got a question in the chat, which was, what was the project that inspired you into making this library?
So I guess the first one, it was a co-range a long time ago, years ago, inspired me to get back into game development. And it was a C engine with OpenGL. And I'm like, that's really exciting. So I copied a lot of its ideas and put them into my words. And I got so far, and then I kind of lost the passion. I didn't know how to bring it to a game. And so I tried again with the GFX HAL library, and I got pretty far, but I was doing kind of, end user cases. And I didn't know how to make a solution out of that. And so if you saw the last graphics talk about the lessons learned from GFX HAL, I think one of the ideas was to kind of fit more to the API and the actual use case at hand. And so when I saw Kajia recently, which is the most amazing project in open source, in my opinion right now, it just showed me how I could take a very fixed function library I had before and turn it into a dynamic graph-based library. And it's like, I see the answer. So I took some of those ideas, and I took a couple ideas from Granite, which is a C++ library, and I put them together, and this is the result. I feel like I just copied them from the internet, but I'm so happy with the result, and that's where we are today.
Cool. I have a question myself, which is a little spicy. Is how are you dealing with the unsafe problem? Are you keeping the library safe, or are you what? Yeah.
Yeah. So the problem is using Vulkan, of course, everything is just a bunch of data that can blow your entire computer in half. And how do you do that? And it's easier, I found, in some parts of the API than others. One of the troubles I had when I was just writing raw Vulkan and making graphics applications and games outside of this project was getting render passes correct. And most of those issues you could find in the validation layers. And so, some of those places I decided not to put a lot of work into making safe inside of Screen 13, because that's kind of like the responsibility of any graphics programmer to get right. But at the same time, ray tracing is almost impossible to do anything at all without crashing the graphics card, because you're passing raw pointers around by design. And in those areas, I cannot make it safe. It's almost impossible to do that. So I tried to split an even line where if you understand Vulkan and you found it to be difficult, this library helps you do it safely. It takes away the things that are most dangerous, barriers, synchronization, render passes, subpasses, descriptors, pools, and makes those things very, very safe to use. But of course, underneath, there's unsafe code everywhere. That's the nature of the beast.
Of course. You touched on this next question, which do you support multiple subpasses?
Yes. So that's logic that I kind of coded, but really copied from Granite. And I'm just, it was a great piece of learning out there. And so I don't feel bad about doing that. It's open source. I feel great. But it's also kind of amazing because I could have never thought this up. So the logic inside Granite allows for taking render passes that have compatible inputs and outputs and either preserving them through a subpass or joining them up and making them part of an actual subpass group. So you can do all of that stuff, keep your rendering on tile, and to you're just defining individual blocks of like, hey, I need to blur a texture. And if it happens to, in the graph of things, work out that it turns into another image later and can be transient, that's something that you can just let happen, so it's not something you have to actually program in.
Cool. That sounds lovely. Thank you for sharing. And unless there's any last questions, I think we're ready for the next talk.
All right, so hello everybody. Welcome back to the final talk for today. And I just want to mention before we dive in that this is just a reminder, after the meetup, we will be hanging out in the Rust Game Dev Discord. If you want to speak, or if you want to talk with any of the speakers, I put the link to the Discord in the comments here, so you should be able to find it through there. But without further ado, I will pass it over to Connor for the final talk today.
Yeah. Thank you so much. And 1 second, I am like all in host mode. Okay. Cool. Does this work? It works. Cool. So, this is my talk on optimizing WGPU with data-driven design. This is actually has some relevance to what we talked about in the last talk, and this talk will be talking a lot about barriers, how WGPU deals with them, and the challenges that come with presenting a safe and stateless API on top of a very stateful. It's not literally stateful, but things like barrier buffers have state in them, on top of a stateful API. So, who am I? I am CW Fitzgerald. I go by this parrot on top of my face all over the internet. I am a professional graphics and game engine developer. I'm currently the co-maintainer of WGPU and the BDFL of Ren 3, which is a WGPU 3D rendering library. Now, for those who are unfamiliar, WGPU is a safe, portable, and modern GPU API in Rust. While it is based off the Wgpu API, it runs natively on top of Vulkan, D3, 11 and 12, Metal, and OpenGL. It has become the de facto standard for GPU access in Rust. There are many, many both projects and libraries that are using us. Bevy, Valoran, GGEasy just moved over to WGPU. So this has become a very core library for being able to talk to the GPU and do any kind of graphics or sort of lighter compute work when you can get away with Vulkan compute as opposed to CUDA. So, if you've ever used WGPU and you've come across, you want to profile your app, you want to figure out what's taking up all the time, you'll go and profile, and there's a decent chance you'll see this one method, or in this case, this one span, taking up a good majority of your time. It's called run render pass, and we've had this mentioned in previous Rust game dev meetups, where the majority of the time is spent in run render pass. This is very consistently a fairly large bottleneck in user applications. Is us doing the work to encode the render passes that the users are writing. Excuse me. So this is a very big function, and if you actually look in the source, it's like 4,000 lines long. But we have to really understand what WGPU is doing for the user. And we present a safe API. And we're presenting a safe API on top of multiple very deeply unsafe underlying graphics APIs. Vulkan, DirectX 12, all, if you go off the rails and you disobey the spec, like, you are safely in UB land, can cause seg faults, can cause all sorts of nonsense. So we need to manage all of the problems so that when the user writes safe graphics code, it gets translated down and safely gets safely implemented on top of the underlying APIs. And in order to do this, there's a couple different things we have to do. We have to manage resource lifetimes. We have to generate barriers, which is something that was mentioned in the last talk. And we also have to prevent race conditions on the GPU. So resource lifetimes is fairly, it's not simple, but like it's fairly straightforward. GPUs are asynchronous. When you submit work to the GPU, it doesn't do anything immediately. It just sends it off onto this queue, and the GPU will get to it when it has some time. Which means and as part of a rule on all of the underlying APIs, you cannot clean up resources until the GPU is done with them. So if you submit and then you immediately drop all of your resources, you drop the device, you drop the buffers, the textures, everything, we can't delete them yet. That would be undefined behavior. So we must keep them alive until at least until the GPU has finished accessing it and all of the references to those objects have died. There's a lot of intricate details about how to manage resource lifetimes and the countless exceptions there are, but this is sort of is out of scope for this talk, so I'm not going to be focusing on this, but this is something to keep in mind and something the structures that I'm talking about in this talk also deal with, and I will mention that when we get there. Second is barriers. GPUs are racy. That's just sort of an inherent property of them. A lot of GPUs are able to do multiple things at the same time. So, for example, AMD is pretty famously known for being able to run a compute dispatches at the same time it's running render passes, even on the same queue. The issue with that is, say that you have a dispatch that writes to a buffer, and you have a render pass that reads from that buffer. There's now a dependency there. So we need to make sure that we insert barriers such that the GPU waits to start the render pass until after the compute pass has fully finished, and most importantly, all of the memory that the compute pass has written has flushed from the cache, so that when you actually start the render pass afterwards, the data will actually be buried. It won't be the previous value before the write happened. There's also some caveats not caveats. There's also some complexity with regards to textures. GPUs have very different representations of textures depending on how they're reading them. Sometimes they have, if you're rendering to them, if you're binding them as a storage texture, those all have different actual binary representations. And you need to issue barriers so that the GPU has an opportunity to rearrange the bits of the texture into whatever the next usage is going to be. In general, I'm going to refer to barriers as transitions, that is what we refer to them internally, but they're the same thing, essentially. Finally, we have to prevent race conditions. This is just one of those contracts that comes with Rust. It is racy to read something while you're writing to it. And this includes sticky situations where you have the same shader is reading the same resource as both read and write. For example, if it has it as a uniform buffer and a write storage buffer, that is an illegal condition because you can't be in both of those states at the same time. It's the same thing as with Rust. You can have a mutable access, XOR, and multiple immutable accesses. And that's the same thing with Wgpu and the same thing with the underlying APIs. So that was a little bit of context about why Wgpu has a bunch of stuff to do. And this is one of the ways we get these things done. These are the trackers. The trackers are responsible for keeping resources alive. All of the trackers I will show own the resources that they track to make sure they stay alive for the amount of time they should. And their other job is to keep track of what state the resource is in, so that we can insert transitions in order to make sure the resource is in the right state at the right time as the GPU is running down the code. Particularly the trackers that are in version 0.12, which is the current released version of Wgpu. The details have evolved and were refined over many years, but largely structurally unchanged throughout Wgpu's lifetime. The core idea worked, so we just ran with it. So the way the trackers work is essentially hash map based. All resources in Wgpu have IDs, and we have a hash map from the ID to the current resource state. That's about it. For example, the buffer state is a bit flags of all the various usages you could possibly have for a buffer. Uniform storage read write, etc. And then we keep track of the ref count of the object and the beginning and end state of the object. We'll get to that bit in a bit. All right, so that was a fairly abstract view. Let's walk our way through how Wgpu does resource tracking, from you creating a bind group to you submitting you submit to the queue, but the real secret is the queue is the device in Wgpu. They're the same thing. So as you submit to the device, there's a lot of points of nuance. If you really comb through this presentation, you will find things that are technically wrong that I've oversimplified. That is intentional because we would be here all day if I tried to explain everything. But this is a good overview of the flow of the data through Wgpu. So you have a bunch of resources, you make a bind group because you want to bind those resources onto the bind the resources to a shader on the GPU. I cannot talk. So as you go through and you create this bind group, the resources are added to the bind group's tracker. The bind group's tracker owns it, so it makes sure that the resources do not die until the bind group itself dies. And then the tracker stores how the resources are used. In these diagrams, I'll be using purple to represent inclusive states. This is similar to Rust's shared references. You can have resources in multiple inclusive states at the same time. However, red represents exclusive, which is the same as a mutable reference in Rust. You can only be in one exclusive state at any one time. So in this example, we have one texture, 3 buffer, or actually we have 2 buffers and a sampler. The texture is in the storage read state. The buffer 0 is actually in 2 different states, in vertex and in uniform, which means that I just realized vertex buffers don't go in bind groups, but just bear with me. Pretend they do for a minute. Pretend that's another inclusive state. And then we have it in uniform state as well. Buffer 12 is in a storage read-write state, which is an exclusive state because it is writable. And samplers don't have state. They are stateless, but they are still tracked because we need to keep them alive. Oh, nope. Wrong direction. Cool. So you take this bind group and you bind it into a render pass. And render passes are special in that an entire render pass counts as 1 unit of synchronization. So every single resource you bind inside a render pass is treated as if you're using all of them at once. And this is so that it is actually invalid to have barriers inside of a render pass. So we cannot possibly have multiple different states that we transition between. So this whole render pass has to be basically one contiguous state. This is referred to in the code and the spec, the Wgpu spec, as a usage scope. So this is a render pass is 1 usage scope. And because of this, render passes can execute completely concurrently. Every single triangle. Well, I shouldn't say that. That's not true. But there's nothing blocking anything from being executed in any order. There's no barriers. Everything will be run contiguously. All the draws are potentially running at the same time. So when we bind this render pass, we iterate through the. Sorry, my dog is barking. Iterate through the bind group, and we add all of the resources stored in the bind group to the various trackers. So the texture, we add the texture to the texture tracker. We go through the buffers, and if you notice that buffer 0 is used in 2 different ways. And so we actually, because they're both inclusive, we can merge them and say this buffer will now be in both the vertex and the uniform state at the same time. This is valid because they're inclusive. And then finally, for buffer 12, we say it's in the storage read-write state. Samplers are a little more complicated, and I won't go into those. So let's say we take that buffer 12 and we turn it into a buffer 0. So we're now using this buffer 0 in 3 different ways. The problem is we can't actually do this because one of those states is exclusive. So if we were that would be a race. You would be able to write to the storage buffer and at the same time modify both the vertex and the uniform ones as you're reading them. And this is a very bad thing. There's also a lot of caches on the GPU are very non-coherent. They're not like CPU caches at all. They have to be very explicitly flushed. So you'll get a bunch of weird stale data. It will be a nightmare. So we cannot allow this. And this is another part of what the trackers do is as they're merging in these states, they need to make sure that the resulting state is valid. Vertex and uniform is a valid state, but vertex and uniform and storage read-write is not a valid state because storage read-write is exclusive. Okay, so we have successfully recorded all these commands onto the render path, and now we need to we are in the process of finishing out the render pass and adding the render pass to the command buffer that you're encoding onto. I wrote a note that it's a smidge more complicated than this. Sort of goes without saying throughout this whole presentation. So what we do is that while I'm focusing purely on buffers here for simplicity. So this is the result of, yes, this is the result of this buffer tracker here. And we're just looking at that as the result of the render pass. So we iterate through all of the buffers that are in the render pass, excuse me, and then we compare them to what the command buffer currently has in its tracker. So earlier in this command buffer, apparently, it used buff 0 as a vertex and uniform. It used buff 7 as a uniform, etc. So this is stuff that has already happened on this command buffer. And remember that command buffers are sets of commands that run in, not in serial, but in order. So this is stuff that happened before. So we see that, okay, so buffer 0, it's the same state as it was before. It was in vertex as uniform before, and it's in vertex as uniform now. And so we don't actually have to do anything. However, buffer 12 was previously used as the destination for a copy. Now we need to use it as a storage read-write buffer. So we need to issue a transition. I wrote buffer 7, that's not right. A transition on buffer 12 from copy, the destination of a copy, to a storage read-write. And this happens before the render pass executes. So you have all the stuff that happened before, we issued this barrier, and then we go through and the render pass will be run once this is the transition has happened. There's a couple more rules about ordering. Some, for example, if you have 2 storage read-writes in a row, you have to still insert a transition because you need to make sure all the writes that happened before the writes on the new render pass, but that's beyond here. So I simplified. So we've now merged the render pass into the command buffer, and now we're looking at the command buffer as a whole. So I represent the command buffer as a single tracker, but it's actually 2 trackers. So you have one at the beginning and one at the end. And if you think of a command buffer is basically a set of operations. And this, at the very beginning of the command buffer expects that resources are in a particular state because that's how they're going to be used. So, for example, in this one, at the very beginning, the 12th buffer is going to be used as the destination for a copy. So as you're going into this command buffer, the command buffer expects that the resource is in this state. So we have this beginning state and this end state. And this gives us the span, sort of the span of states, when we literally use Rust's ranges for this to represent the before state of the command buffer and the state that the command buffer leaves the resources in, if that all makes sense. If any of this doesn't make sense, please ask questions at the end. I will gladly answer them because this is a lot. I'm throwing a lot at all of you. Finally, you take this command buffer, you finalized it, and then you go to actually submit it to the device/queue. We need to do 2 different things. We first need to look at the state of the resources on the device. This is what the actual device, or what the actual resources is, the state of the resources are in after the last submission. So we've done the submission, we're now doing this new submission, and we need to look at the command buffer we're submitting and compare the trackers and say, all right, so this is what they're in before, and this command buffer expects that all of these resources are in these particular states. So we need to first insert barriers or transitions in between the last submission and this command buffer in order to transition all of the states into what the command buffer expects. Once we've issued that, we then need to update the end tracker. We need to update the device with the new state. And we've transitioned into the beginning of the command buffer, and now we assume the command buffer runs, so we need to grab the state at the end of the command buffer and update the state in the device to say, we've now executed this command buffer, all of these resources are now in this end state as opposed to the beginning state. That is why we store both states in a command buffer. Hope that all makes sense. This is crazy. All right, so I think I was a little cocky when I said it was fairly clear to understand. There's a lot going on. Again, questions at the end. This is all fine. What's the problem? It's slow. Almost all of the program time is spent inside of run render pass, basically inside of the texture tracker. And this is a report from vTune on some program. I don't remember which program I was using to benchmark. There's a couple I was using. But as you can see, it's inside the merge function of the texture tracker, or inside of run render pass, or inside of our range system, which is another thing. That's another part of the texture tracker. So basically most of these are part of the texture tracker, or this, for example, this vec call is actually part of texture impl2 merge. So this is all part of the texture tracker. So this is a problem. This needs to get faster. So I went to vTune, did a bunch of testing, and the result is we are getting absolutely destroyed by memory access. CPI is a unit of clocks per instruction. You're normally used to seeing this as instructions per clock. CPI is the inverse of this. And that means, for example, this lovely hash brown function has a CPI of 14. That means that it takes 14 clock cycles for the CPU to dispatch a single instruction. In the ideal world, CPUs can generally dispatch 2 to 3 instructions every single clock cycle. So your CPI should be about 0.3. A lot of these functions have CPIs above 1, which is not only is very bad, but in the 2, 3, 5 range, that means that we are just getting completely annihilated by our memory access. So, how do we make our memory access faster? How do we fix this? Forgot that slide was there. Here's part of the problem. Texture trackers are giant. Textures are complex. You can have a texture with multiple bitmaps, with multiple layers if you have, for example, a cube map or a 2D array texture. And we have to keep track of all of them because you can take each, what they're called sub-resources. So a mipmap and a layer, so mip1 layer 1 is a sub-resource. Mip2 layer 1 is a sub-resource, etc. So all of these things are individual sub-resources. You can use them as if they were independent resources. So we have to track all of that. Because of this, the texture tracker is giant. It's nearly 0.5 kilobyte. And we're storing this inside of a hash map. And that means every time we look up in this hash map, it's basically a guaranteed cache miss. We're doing essentially random access into this very large data structure. We're going to be cache missing left and right. So I actually already explained most of this. Each sub-resource can be used independently. It's a very classic example to use to generate bitmaps on the GPU, where you read from one bitmap and write to the other. Then once you've written to that one, you read from it again and write to the next one down as you generate the whole MIP chain. However, if you actually look at the usages that people are doing, most resources are in a single state for the whole resource. Even, for example, if you're uploading a cube map, you have to upload each individual layer of this cube map independently. But once you're done with that, You just use it as a texture to sample from the whole time. And, it's not being changed, it's not being modified. There's no real point in tracking each individual state of this cube map if it's just always going to be used as a whole resource the whole time. There's a couple use cases where you have to use every state differently, but the important part about that is that very few textures actually are in that state. They're generally shadow textures, any kind of sort of things you render to are generally in complex states. So with that in mind, we can optimize our representation of texture states. And we can split it into two parts. We can say that a texture is in a simple state or a complex state. A simple state is the whole resource is used in one way. Very common, happens all the time. And then we can have complex states, which have individual states for each sub-resource. And because of the frequency, we spend the majority of the textures we track are in the simple state, which means we only actually need 2 bytes to store every single bit of information about the state of the texture. Compare that to nearly 500. That is a very, very clear improvement. Second, the issue with hash maps. And the first instinct is, oh, it's the hash. The issue is almost never the hash, at least in our case. In our case, we use keys that are like U64s. So they're very small. Hashing them is very cheap. We use a very fast hasher because we're concerned about that. Excuse me. So the issue with hash maps is not the hasher. The issue with hash maps is the nonlinear memory access. So bringing back this example, we iterate through the right-hand side and we look up on the left-hand side. Now, depending on the particulars of the hash map and the hash algorithm, but consider that hash maps actually have randomness in them. They are they actually pull a random number when you make a hash map in order to basically randomize the hash state. And because of this, 2 hash maps with identical contents do not store the data in the same order. So as you're iterating through one of them, you're doing essentially random access into the other one. You're jumping all around this. Hash maps are stored in their underlying implementation as a vector. You're indexing into this. You're indexing into this buffer all over the place. So the CPU has no idea what you're doing. It can't predict what you're doing. It cannot. It's basically clueless every time, and as a result, will eat a lot of cache misses because it can't use something like the memory prefetcher, which will pull in memory before you need it if you're doing a simple access, like a linear scan. So, welcome to this. Well, I've been going over how the existing trackers work, and these new trackers work the same way. They do the same operations. They do the same do the same work. They are just structured differently. And they're structured by exploiting how Wgpu IDs work. All of our IDs are unique. They are unique at any one time. So if you make a buffer, it gets a unique ID. If you destroy that buffer and make a new one, we reuse that ID. We have an I don't know, is epoch, epic? I don't know. We have one of those to make sure that IDs don't get mismatched. But at any one time, there should only be one resource that has that ID at any one particular point in time. So we can use this ID as an index into a vector. And because we reuse them and we intentionally keep them as low as possible, we can make a buffer and just use that ID as an index. So this is what the new double-ended buffer tracker looks like is it is completely structure of arrays. It has multiple arrays for the beginning, the end, the ref counts, the epochs, and it has a bit vector for whether or not a resource is owned by that tracker. Because remember, before there were hash maps, so we could just not put something in the hash map if it's not owned. But now that we have a slot for potentially every single resource in WGPU that's currently active, we need to say, is this resource actually here? So merging trackers is now a linear operation, which is actually slightly worse than before. Before, trackers merging was linear on the size of the input tracker. So for example, the render pass, as we merge the render pass into the command buffer, we only have to iterate every element in the in that render pass. Now we have to iterate through all of them because we don't actually, it's not sparse. So it's not like we just iterate through and we get only the ones we want. We get all of them. So this sounds worse. How is it better? Running down arrays is very, very, very fast, especially if you have a very small amount of data. And if you notice, every vector here is trying to be kept as small as possible, using as little data as possible, and it's stored in an SOA way so that we don't waste any bytes. So as you're iterating down these things, you use every single byte that you load from memory, and because you're iterating down arrays, the memory prefetcher knows exactly what you're doing and can start prefetching immediately. Now, the double-ended texture tracker is a little more complex, same idea, but now we have this separate sidecar data structure, which is, again, a hash map from ID to this complex texture state. When we say a resource is in a complex state, there's actually a texture use called complex, which doesn't actually get used in practice. It's not like storage or uniform, etc. But signifies, hey, this texture use is not valid. Go and look in the complex tracker to get the actual complex state. So we can store it in a nice tight U16 bit flags, and when we need all of this complexity, we can go and look it up in the hash map, find all of the various information there. So this is a hybrid sparse and dense model, and lets us get the best of both worlds. And remember, most resources will never touch the complex tracker at all. That's just there when we have to. And finally, another component of this is that we're using a bit vector for ownership. So let's say we have 50,000 total resources in the world, but we have a render pass that uses one of them. Obviously, we don't particularly want to iterate through 50,000 different states, see that they're all empty, and then skip them. So because we're using a bit vector, we can actually optimize the sparse case, and because we can load a single usize from this bit vector and say, is this 0? If it's 0, none of the resources are there. So we can skip that whole block of 64 by only reading 8 bytes, which means if you have only run one resource used in this whole thing, we only have to, despite 50,000 resources in the whole system, we only have to check about 6 kilobytes of memory. And 6 kilobytes of memory, if it's hot in cache or very well prefetched, goes very, very quickly. So this is how we get away with the dense model, despite in the logical sense, our storage is sparse, or our task is sparse. So this is where I put my money where my mouth is. These are the results. I'm testing this against RIN 3, mainly because it was the easiest one to upgrade to the Git version of WGPU, because I wrote it and I know how it works. So that wasn't very hard. This is a notoriously complex scene. It has tons of extra geometry. Every object you see has like 3 objects within it for no reason because I exported it poorly. But it's a great test scene. So, in terms of raw frame time, Ren 3 has both a GPU-powered mode and a CPU-powered mode. CPU-powered is very traditional. You bind groups for every single object. You call draw, do it again in a loop. GPU-powered is much fancier. It renders the whole scene in 3 different draw calls using bindless. But after the the new texture trackers have been implemented, we saw in terms of raw frame time a 2.5 times speed up and a 1.7 times speed up respectively because of this improvement. Now, note, this includes all other work in the program, and this program is doing a decent chunk of work outside of Wgpu to prep all the state and push that all up, etc. So let's look at some more submetrics. In terms of run render pass time alone, CPU powered, we're getting a 3x speed up. GPU powered, we're getting a 7x speed up. From 70 to 23 milliseconds, and from 780 microseconds to 110 microseconds. And inside of run render passes is one function called insert barriers, which is the thing that is actually doing the iteration over every single thing in the render pass and adding it to the command buffer. And this particular function sped up 14 times, and it is the same in both CPU and GPU mode. We're now down to 7 microseconds for this particular benchmark. This is incredible. It is very quick. Finally, we have some synthetic tests. This is what I was using to sort of as a unit test for these optimizations. We're looking at buffers and textures. This is a little dense. So I will explain them. So we're looking for the buffers. We have a single bind group that has 10,000 buffers in it, and 10,000 bind groups, each with 1 buffer. And as you can see, and the same for textures. And as you can see, the improvements were more for the single bind group case, but no matter what, there were improvements. The texture tracker, because of this complex to simple state change, we got tons and tons of speed up there, from 7 to 13 times speed up, whereas buffers was a little more modest, but still significant, of 1.4 to 1.7 times speed up. So this is all absolutely music to my eyes, and yeah, so now what's next? We've made a lot of progress. We've done a lot. What is next to go? Profiles still show hotspots in the code. And I'm not going to get into the particulars of this because I haven't verified. Profiling loves to show red herrings, so I haven't verified any of this. But there's still many hotspots showing in the code that we need to improve on. But as we squeeze this tighter and tighter, guaranteeing improvements gets harder because you start to get to the point where sometimes the things you do to make things faster take longer to set up than actually just doing the thing. And we also have to scan over a wide variety of use cases to make sure that we aren't pessimizing some use cases, because that would be even worse. Wgpu is still plagued with locking issues. We've had long-standing multi-threading problems, which are next on the docket to solve. To an extent, speed losses inside of render pass running can be helped through multi-threading, because you can in theory run multiple render passes on different threads and then submit them all at once. And finally, This sort of locking project is a follow-up to the organization with a different approach, which I'm totally not going to get into because I could also talk about this for about 30 minutes. So, why is performance important? Besides the obvious reason is going fast is good. We only actually advertise that we are portable and safe. And those are the things that we have focused on to this point. That's not to say that we haven't kept performance in the back of our mind and tried to design all of our structures in a way that is efficient and works as quickly as possible. But our promise to the world is that your code will work everywhere and you will do it in completely safe code. However, we need to be fast because we need to keep users confident in us. When people are saying that WGPU is too slow and they go and use Vulkan, they go and use DirectX 11, they go and use DirectX 12, that means we aren't doing our job correctly. People will start to look at us and be like, well, that's cute, the portability is cute, but I need the performance. And the confidence in us will slowly start to erode. And so this is, now that we've gotten to a place where we are making good on our portability and our safety guarantees. We have bugs, of course, but we're, for the most part, doing a very good job of this. We really need to focus on speed. Ultimately, WGPU wants to be the best portable graphics API out there. And ultimately, we will be. We will get there. So, yeah. If you like the work that I do, I am on GitHub sponsors. I do all this work in my free time. So no pressure at all. If you don't. Yeah. I totally got my brain. Links to things. There's this is the first time that I've actually talked about something that hasn't actually been merged in yet. The PR is still outstanding, but it will eventually go in. We've linked to WGPU and the slides, and I will also post both the slides and the diagrams I made in the Meetup GitHub once we get there. And finally, thank you again to Quark for his continued support through everything, and thank you to the WGPU, Rust game dev, and Bevy communities for being so continuously supportive. Questions?
Great. Well, thank you so much for that. I mentioned in chat here, but it wouldn't be a CW Fitzgerald talk without a portion halfway through showing amazing numbers and speed of some benchmark. So it's like we get all the theory and then it pays off and we see like all the improvements. Always lots of fun. A question in chat, and this might have been related to a specific part of the talk, but I'll ask it verbatim. Does the texture split state also result in memory savings here on the CPU?
It's a wash, kind of. Memory was sort of never the problem. We didn't, like, even with 50,000 textures, all in complex states, that's 25 kilobytes, which is basically negligible. Even across 100 command encoders, like, that's, was that 2 megabytes? Doesn't show up in comparison, so I wasn't really thinking about that. Because we now store data in a dense way, we also do waste space because we have to store these 50,000 element long vectors everywhere. But all in all, the memory used is actually not significant. The issue is mainly around cache utilization. So I actually just flat out don't have numbers on that because it was never really a problem.
All good. Another one that I was sort of wondering about myself, and it was partly answered in chat, but I'll get you to give a different answer, is when it comes to a lot of the optimizations and stuff we talked about today, how much of this type of stuff needs to be exposed to the end user as something that they need to sort of pay attention to themselves?
Absolutely zero of it. This is all completely internal APIs that we use to provide the guarantees that we do. We you don't have to think about any of that.
Nice, good stuff. And let's check the game dev Discord as well, because I told people there that they could ask questions. Okay, so one question, and maybe this was like sort of answered a little bit already, but how will this impact the rest of the Rust game dev ecosystem? And I guess that's a pretty broad question.
Yeah, so your code will get fast. If you use Wgpu, your code will get faster. That's basically the long and short of it. Nothing fancy beyond there. Yeah, Wgpu will be faster now.
Yeah, and I think from my perspective as like a downstream user of WGPU through Valorant, where I don't actually touch any of the graphics code. Like we have very smart people that do that, but I get to play Valorant at faster FPS, and so yeah, I think that is definitely being downstream is a very nice place to be. All right. Does any of this help with mesh loading and texture loading at the Ren 3 level, slowing down the render loop?
No, that's a different problem. I'll follow up with them independently.
Sounds good. And then I guess so. Ren 3 is directly using WGPU, right?
Yes.
And so, are you able to use like Ren 3? Like, do you use it as like an example of what could be improved in certain ways, or like you having done Ren 3 gives you ideas on WGPU, or what's how is like the symbiotic relationship work there?
Yeah, very much that way. This is actually driven by performance reports that I get in Ren 3 saying, "Hey, I like upgraded the version of Ren 3 and performance got worse." And so I started investigating that, and one thing led to another, and I ended up at this this is the bottleneck that needs to be eliminated first. Is this everything inside run render pass, and to an extent, it's still the bottleneck. It's just faster now. So there's still more to go. As I said, there's still hot spots to squeeze down. We are continuously improving. But yes, Ren 3 has driven a lot of the improvements that I make to WGPU because it makes things. People use it, and when people use it, they spot issues, and I bring those issues down to WGPU to make everyone's life better.
Nice. Another question: couldn't the state changes, or at least some of them, be tracked directly when recording the render pass instead of doing it at queue time?
That is a very good question, and the answer is no. The thing is, if you're recording a render pass, you're recording a render pass onto the command buffer, and you could, for example, run a render pass on command buffer 1, run a render pass on command buffer 2, and then submit them in the other order. You can submit the second one first, and then the first one second. And because of that, we don't actually know the full chain of states on the device until you submit. We do know it in the command buffer because the command buffer is a linear set of commands, but we don't know how those command buffers actually merge together onto the device until you submit. So we can't do that immediately, even though we would love to. In an API like GL, you could, because there is a single global state, but we know that that is horrible for many reasons. And this also lets you do things like parallel command recording, where each command buffer runs separately. There's an interesting point to be made. Things like APIs like Dawn. Dawn is Chrome's implementation of Wgpu. And Dawn actually defers all of this until submit time. They don't actually record their command buffers until you submit the Wgpu command buffers. And this allows them to have a much more global view and have a single, I can see all the states at once, which is useful to an extent. But it also means that you don't get the benefit of the user's able to multi-thread. The user can now take a command buffer, record it over there, record this over there. all on their own, and then submission is a fairly lean process for us. Whereas with them, they have to go and actually record all the command buffers for all the work that they did. There are pros and cons to both of these, but for us, being able to give the users as much control as possible to make us as much like the native APIs is very important to us. So to an extent, we inherit more complexity in order to give the users that guarantee.
Great. And so I think that's it for questions. And so we will end off the meetup here for today. But Connor, thank you so much for the talk. It's always great having like these longer form ones, and I definitely want to see more of them in the future. Yeah, so with this being the end, we'll move over to Discord now. So if you want to speak with, or if you want to chat with any of the speakers, if you want to ask any more questions, feel free to join the link. I'll put it into the Twitch and YouTube chats again. But yeah, Connor, any last words from you?
No, thank you for having me, and this was wonderful.
Absolutely. All right, we will see everybody next time.